Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the third numerical on digital modulation techniques. Please note this is a numerical on binary frequency shift keying. Let me read out the question first. Binary data are transmitted at a rate of 10 to the power 6 bits per second over a microwave link. Assuming channel noise is AWGN with 0 mean and power spectral density at the receiver input as 10 to the power minus 10 watts per hertz, find the average carrier power required to maintain an average probability of error PE less than or equal to 10 to the power minus 4 for coherent binary frequency shift keying technique. Determine the minimum channel bandwidth required. Let us start with the solution part. We are told it is a coherent binary FSK system. The data rate RB is equal to 10 to the power 6 bits per second. The power spectral density at the receiver input, which is N0 by 2, is given as 10 to the power minus 10 watts per hertz. And the average probability of symbol error is said to be less than or equal to 10 to the power minus 4. Here we are asked to find the average carrier power P for the given values of RB, PE and N0 by 2. Right. Let us now start with the equation for the average probability of symbol error for a binary FSK system. PE equal to 1 divided by 2 ERFC of square root of EB divided by 2 N0. Right, I will call this as equation 1. Now, we are given the probability of error should be less than or equal to 10 to the power minus 4. So, I am going to now replace PE with 10 to the power minus 4 here. Then I will substitute the remaining values here. It is equal to 1 divided by 2 ERFC of square root of EB is not known, N0 is known, but however I will just keep it as it is for time being. Rewriting this equation, I will obtain ERFC of square root of EB divided by 2N0 is equal to 2 into 10 to the power minus 4. Now, please note this is in the form of ERFC of U is equal to 2 into 10 to the power minus 4. So, we have to now find the value of U for which the ERFC of U is 2 into 10 to the power minus 4. We know that ERFC and ERF are complementary. In simple words, ERFC of U can be written as 1 minus ERF of U, where ERF stands for simply the error function. So, this is equal to 2 into 10 to the power minus 4. Therefore, ERF of U is equal to 1 minus 2 into 10 to the power minus 4. This is equal to 0.9998. Now, I have to go to the error function table and find the value of U for which the ERF of U is equal to 0.9998. Let us go to the error function table now. Right. This is the error function table, and upon searching the table carefully, we will find that the nearest value for 0.9998 occurs for U equal to 2.5. So, we will now say that the value of U is 2.5. Now, let us go back to the numerical, and here I will write U is equal to 2.5. Once we find the value of U, let us substitute for U. What was actually U? Please note, square root of EB divided by 2N0 was U. So, I will therefore write square root of EB divided by 2N0 is equal to 2.5. Let us now simplify this to find the value of EB. Therefore, EB is equal to 2.5 square multiplied by 2 multiplied by N0. Let us substitute for this. it is 6.25 multiplied by 2 multiplied by the value of n naught by 2 is 10 to the power minus 10. Therefore, n naught is equal to 2 into 10 to the power minus 10. Upon simplifying, we will obtain this as 25 into 10 to the power of minus 10 joules. This is the bit energy. Please note, in our numerical, we are asked to find the average carrier power. So, let us now continue to find the carrier power. I will represent the carrier power by capital P. Now, we know that the carrier power P and the bit energy are related by the equation P equals EB, which is the bit energy, divided by TB, which is the bit duration. Here, the value of TB is not specified, but we can compute the same using the value of RB. We know that TB is equal to 1 divided by RB, and RB is given as 10 to the power 6. So, TB is equal to 10 to the power minus 6 seconds. Let me now substitute it back into the equation for P. Therefore, carrier power P is equal to EB, which is 25 into 10 to the power of minus 10 divided by TB, which is 10 to the power minus 6. So, this is equal to 25 into 10 to the power of minus 4 watts. This is the value for the average transmitted power or the average carrier power. Now, very importantly, when we come back to the numerical, please note we are told the average probability of symbol error must be less than or equal to 10 to the power minus 4. We know that the average carrier power and the probability of symbol error are inversely proportional to each other. Therefore, to make sure the average probability of error is less than or equal to 10 to the power of minus 4, the average carrier power P must be greater than the computed value, which is 25 into 10 to the power of minus 4 watts. Therefore, I will write it here as to maintain PE less than or equal to 10 to the power minus 4, the average carrier power P should be greater than or equal to 25 into 10 to the power minus 4 watts. That is about computation of the average carrier power. Coming back to the numerical, please note we are also asked to determine the minimum channel bandwidth required for the coherent binary FSK system. Now, this is pretty simple because the minimum channel bandwidth required is simply is equal to 1 divided by the bit rate. 1 divided by TB, which is equal to 1 divided by 10 to the power minus 6 equal to 1 megahertz. This is the solution for this numerical. Right, that is the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.